Okay, so today we're going to talk about one last thing before we finish up the semester, and that is Maxwell's equations of electromagnetism, which are mostly just a reframing of laws of electromagnetism that we've already looked at. So I'm going to start just by reviewing the laws that come together to form Maxwell's equations, and then we'll talk about Maxwell's contribution to electromagnetism of something new. So the first one of Maxwell's equations is really just a reframing of Gauss's law. We saw Gauss's law like this: the integral of E dot dA over some surface, the electric flux through some surface, is equal to the charge enclosed divided by epsilon 0, this constant of electromagnetism that we encounter in all of our E&M equations. That's Gauss's law. We didn't really give a name to this next law, but we talked about the fact that magnetic fields always originate from a north pole and end at a south pole. And there's no such thing as magnetic charge per se, which means that any surface you draw in space with magnetic fields involved, the amount of electric field lines going out of that surface is going to be equal to the amount of magnetic field going back into that surface. And the integral of B over that surface is always going to be equal to 0. We can call that law of physics Gauss's law for magnetism if we want. And we can write it the integral of the magnetic field over some surface is equal to 0, because there's no such thing as a magnetic charge, an individual isolated north or south pole. They always come in pairs. The next law that we saw was the law for magnetism, which we called Amperes Law, which says that, I'm going to do these in a slightly different order, the integral of the magnetic field around a closed loop, integral of B dot dl around some closed loop, is equal to mu 0, this magnetic constant, times the current that passes through that loop. And we used Ampere's law to find the magnetic field in some simple situations. So that's due to Ampere. The next law of electromagnetism we looked at was Faraday's law, which says that the EMF in a loop, and we can write that as the integral of E dot dl. We never really framed it that way, but the EMF around a closed loop, we'll just write this, is equal to the integral of E dot dl. Gone off the screen there. The integral of E dot dl is equal to the rate of change of the magnetic flux through that loop, and that negative sign in that law is very, very important. The negative sign by itself is essentially Lenz's law, but this law is due to Faraday. Okay. These four equations summarize pretty much everything that was known about electromagnetism until Maxwell came along. And these four equations, with one modification, are what we refer to today as Maxwell's equations in their integral form. But there's one thing missing, and I want to talk about well, how Maxwell knew this was missing and what convinced Maxwell to put this in. There's a symmetry to these equations that if you look at the fact that electric fields are caused by electrical charges and magnetic fields are caused by moving electrical charges, we can understand why the electric field integrated over some surface area is equal to the enclosed charge, but the magnetic field integrated over an area is 0, because there's no such thing as magnetic charges, individual magnetic poles. We can understand why the magnetic field integrated around a loop is equal to mu 0 times the current, but there's no analogous magnetic current to be in this equation, because there's no such thing as magnetic charges. There's no such thing as an individual magnetic north pole that could flow through space. But this equation, Faraday's law, says that electric fields around a loop and EMF around a loop can be caused by a changing magnetic field. This equation doesn't say that. It says that they can be caused by moving charges, but it doesn't say anything about changing electric fields. And the lack of symmetry here, Maxwell saw as sort of a problem. And we can understand this if we imagine, let's imagine a circuit that's got, say, a battery and a resistor and a capacitor. In our last lecture, when we talked about RC circuits and RLC circuits, we said if we have a switch here and we close the switch so that current starts to flow through this circuit, that the current will start big and gradually tail off to zero as the capacitor fills up with charge. While current is flowing through this loop, let's ask ourselves, what would the magnetic field be in the various parts of the circuit? Well, if the electricity is flowing this way through the circuit, there'll be a magnetic field due to the right-hand rule that will be coming out of the board here and into the board there, because there's a current flowing. Over here, where there's current flowing, there will be a magnetic field out of the board here, into the board there, out of the board here, into the board, out of the board. No. Is that right? Can't make my hand go that way. Into the board here. Yeah, out of the board there. But here, there's no current. Current doesn't flow through the empty space in a capacitor. What there is in the capacitor, as the capacitor charges up, is a changing electric field. Okay, as that capacitor fills up with charge, the electric field between the two plates of the capacitor will get bigger and bigger and bigger. If you ask yourself how the magnetic field should behave in space, what Maxwell realizes, the magnetic field shouldn't just discontinuously stop in space here and start up again. The magnetic field should be continuous, which means that if here the current is creating the magnetic field, that here the changing electric field should be causing a magnetic field. So Maxwell just guessed that it was true based on considerations of symmetry and continuity of the magnetic field, that there should be an additional term in one of these equations that was not discovered by Gauss or Ampere or Faraday. And that extra term looks like this, that the magnetic field created in a closed loop in space is equal to mu 0 times I plus mu 0 epsilon 0 times the rate of change of the electric flux through some loop. This is what Maxwell added. And Maxwell's addition was not based on any experiments he did with wires and batteries and stuff. It was based on his intuition that these equations should be symmetrical and the magnetic field should be continuous. Therefore, if a changing magnetic flux creates an electric field, then a changing electric flux should create a magnetic field. These equations, these four equations, are known collectively as Maxwell's equations. Seems a little unfair, since a lot of the work was done by Gauss and Faraday and Ampere. But because Maxwell kind of collated these all together into a single set of equations that encapsulated everything that was known about electricity and magnetism, we call them Maxwell's equations. And Maxwell made this important contribution to the equation. This is not the form that we usually see Maxwell's equations. These are Maxwell's equations in integral form. By the way, it's worth noting that these are Maxwell's equations in integral form in free space. What I mean by that, we've always been assuming up until now that these electric fields are and magnetic fields are existing in a vacuum, that we're not inside of a piece of copper or inside of a piece of plastic or inside of a conductive solution of sodium chloride. In those situations, the mu 0 and the epsilon 0 are replaced by the mu and the epsilon of the particular medium, the permittivity or permeability of some particular medium. It's beyond the scope of this class to talk about electric fields in matter, so I will file that. You guys can file that away later, and you'll talk about that in some advanced electromagnetism course that you take as maybe a junior physics major. We don't encounter Maxwell's equations in their integral form as often as we encounter them in their three-dimensional differential form. So I want to write them that way as well. For those of you who have taken Calculus 3, this notation will be familiar to you. For those of you who haven't, I'll try to explain what these vector differential operators mean. The first equation, the integral of E dot dA is equal to the charge over epsilon naught, is equivalent to, in differential form, saying that the divergence of the electrical field is equal to the charge density divided by epsilon 0. The divergence is a three-dimensional vector operator. We've only talked about one three-dimensional vector operator before. That's the gradient. The gradient is an operator that operates on a scalar field and tells you the direction in which that field changes the fastest. It turns a scalar field into a vector field. The divergence is an operator on a vector field that tells you how much that vector field's vectors diverge in space. And so it's an operation that you do on a vector field that gives you a scalar. So you can think of it as a sort of three-dimensional derivative that tells you how much a vector field's lines at a given point diverge outward from one another. And what causes a diverging electric field is electric charge. You might guess that if you think about the symmetry between these two equations, that the associated equation for magnetism is that the divergence of magnetic fields is 0. That magnetic field lines don't actually diverge outwards in space and go on forever. They always loop back around from the North Pole to the South Pole. So div B is equal to 0. This law can be written in terms of a vector operator called the curl. The curl is a vector operator that operates on a vector field and gives you another vector. And this law says that the curl of the electric field is equal to the rate of change of the magnetic field, so minus dB dt. And I'll write these derivatives as partial derivatives for now. Okay. So an electric field that curls around in space, what the curl of a vector field measures is how much the vectors either curve around on space or how much sort of rotation they would cause. If you think about, one of the easiest ways to think about this is in terms of a fluid. Imagine a vector field representing a fluid flowing through space. If the vector field has a curl, that means if you put a tiny little paddle wheel there, it would spin. So if you had a vector field like this, where the vector was large there and then small here, and you put a paddle wheel here, okay, the paddle wheel would rotate because it's being pushed harder on this side than that side. So you can think of the curl as a measure of how much the vector field sort of rotates or turns in space. And that makes sense if you think about what this law, Faraday's law, says. It says that a changing magnetic field causes an electric field in a circle around in space that causes current to flow in a loop. So the differential form of Faraday's law is that the curl of the electric field is equal to dV dt. And again, in some junior level electromagnetism course, you will actually learn how to use these vector operators to calculate the divergence and curl of various fields. I'm rewriting this to give me a little more room here. By the way, if you look up Maxwell's equations, you might not see them in exactly the same form. You might see these fluxes written in terms of integrals around a loop or around a surface. Apparently, I'm not moving around enough while I teach, the lights just went off. I had to pause it and turn them back on. So this electric field, since it's about the, or sorry, this one of Maxwell's equations, since it's about the magnetic field, integrated around a loop, is going to be about the curl of the magnetic field. And it's going to have two parts on the right-hand side of the equation. One due to the current, which I'll just write as mu 0 j. We use j to stand for the vector current density, plus mu 0 times epsilon ln 0 times the rate of change of the electric field. And I'll go ahead and I'll write that as a partial derivative as well. Am I still on the screen? I've just barely gone off. I'm going to give us a little nudge that way. Okay, so the magnetic field curl, how much the magnetic field wraps around in space, is equal to mu 0 times the current density, how much electrical current is flowing through space per unit volume, plus mu 0 epsilon 0 times the rate of change of the electric field. These are Maxwell's equations in differential form. Okay, so integral form, differential form. Each of these statements is equivalent to the statement next to it, except written as a derivative, a three-dimensional derivative in space instead of an integral. Okay, so that's great. That's important. Maxwell's equations really encapsulate everything that was known about electromagnetism up until the time of Maxwell in the late 1800s, and they still essentially tell you anything you could possibly want to know about macroscopic electrical phenomena. Not the microscopic interactions of electric fields with individual electrons, but electric fields moving through space, interacting with antennas, and so forth, are all they're entirely explained by Maxwell's equations. You can essentially derive any electromagnetic phenomena or the behavior of any electric or magnetic phenomena from starting from these two sets of equations. Sometimes I tell the story of my graduate qualifying exam, the exam you take when you are testing to get your master's degree or your PhD. It was a 3-day long exam. It was 4 hours on the first day, 8 hours on the second day, 4 hours on the third day. 16 hours altogether, 16 problems. You were guaranteed one, probably two problems about electricity and magnetism. And Maxwell's equations are so powerful and so useful that if there's a question about electricity and magnetism, if you didn't know anything else to do on the problem, the first thing you would do is you would write down Maxwell's equations. You'd get a couple points just for showing that you know Maxwell's equations and that you can use Maxwell's equations as a starting point to pretty much get anywhere to solve an electricity magnetism problem. But that doesn't seem like quite enough for Maxwell to get these equations named after him and for them to be so important. So what I want to talk about next is what Maxwell did with these equations that really actually was sort of revolutionary. Okay, so I want to take a look at the differential forms. And I want to imagine electric fields and magnetic fields in empty space with no charges around, no currents around, just the fields themselves. What does that mean in terms of the equations? This says the divergence of the electric field is equal to the charge density divided by epsilon 0. But if there's no charge, because we're in empty space, then in empty space, this is equal to 0. Okay. Divergence of B is always 0. The curl of the electric field, how much the electric field curves around in space, is equal to the rate of change of the magnetic field. That's fine in empty space. You can have electric fields and magnetic fields in empty space just fine. The curl of the magnetic field is equal to mu 0 times the current density times mu 0 epsilon 0 times the rate of change of the electric field. But if we're in empty space, there's no current density, there's no moving charges, there's no charges, there's no nothing at all. Okay, so these are Maxwell's equations in empty space. in vacuum. And they tell us a relationship between electric fields and magnetic fields. And in particular, these two equations suggest a relationship that is reciprocal, right? The rate of change of the electric field in some kind of complicated spatial way is equal to the rate of change of the magnetic field in time. And the rate of change of the magnetic field in some kind of complicated spatial way is equal to the rate of change of the electric field in time. We can look at this as a system of two equations. We can ask ourselves, can we combine these two equations together? Let's try that. I'm going to do something that's mathematically suspicious. I'm going to take this equation, curl of the electric field equals minus, get myself a little more space there, minus dB dt. I'm going to get rid of the partials for now, just write my differentials as derivatives. I'm going to take the curl of both sides. The curl is just a vector operator. Most operators obey the rule that if you do them to both sides of an equation, that's a legal thing to do. And I'll just ask you to accept for now that that's a legal thing to do. Here we have the curl of the electric field. That actually has a special name. Well, let's not do that just yet. Let's just leave it like this for now. The curl of the electric field. To do this next step on the left-hand side, I have to cheat a little bit, and I have to use some three-dimensional calculus identities that probably even those of you who took Calculus 3 haven't seen yet. But I'm going to kind of wave my hands around and ask you to just accept what happens next. On this side of the equation, I'm going to reverse the time derivative and the curl. Now you might ask, are you allowed to do that? Are you allowed to change the order of that? Because space and time coordinates are independent of one another, just take my word for it that you're allowed to do that. Okay, so this is equal to minus the curl, no, minus dt of the curl of B. Okay, so instead of the curl of the rate of change, I've got the rate of change of the curl. Okay. Through some magic of vector calculus, I'm going to rewrite the curl of the curl as triangle squared. Just think of that as a three-dimensional second derivative, and don't worry about for now what that means. Like I said, if you take a junior level advanced electromagnetism course, you'll see the math in between here, and you'll understand what that operator means. On this side, though, we've got the time derivative of the curl of B. But from Maxwell's equation over here, we know that the curl of B is equal to mu 0 epsilon 0 dE dt. So we've got on this side minus d dt of mu 0 epsilon 0 dE dt. And this is the derivative of the derivative. That's just the second derivative. So what we've got here is some kind of spatial second derivative of the electric field is equal to mu 0 epsilon 0 times some kind of temporal second derivative of the electric field. I've left out my minus sign. Okay? This equation is very important. And if you are a physicist, this equation is very recognizable. Any phenomenon that obeys an equation that says a certain kind of spatial second derivative is equal to a constant times a certain kind of temporal second derivative. If this was just in one dimension, we could rewrite this as follows. We could just write this as d squared e dx squared equals minus mu 0 epsilon 0 d squared e dt squared. Any physicist who's been studying physics long enough recognizes that differential equation as the differential equation for something that obeys a wave function. Okay, so this differential equation is the same differential equation that is obeyed by a string that you tie down at both ends, and you pluck it with a guitar pick, and it vibrates back and forth and makes a wave. It's the same differential equation obeyed by the pressure of sound in a sound wave. It's the same differential equation obeyed by the water as it goes up and down in a water wave. This equation, the second spatial derivative is equal to a constant times the second temporal derivative, a negative constant. If you think about differential equations that we know and actually just talked about in the last video, you know that the equation d squared something dt squared equals minus constant something. You should recognize that equation as having the solution of something that oscillates in time sinusoidally. Right? That's the equation, the differential equation for simple harmonic motion. If we hold t constant here, we have a differential equation that says the rate of change with respect to position of the rate of change with respect to position equals some negative constant times the function of position. So that means if we hold t constant, we have a function where e of x varies sinusoidally with x. If we hold the position constant, then we have a differential equation that says the second derivative with respect to time equals some negative constant times the function with respect to time. So we've got a situation where the electric field as a function of time obeys an equation that varies sinusoidally with time. That is the equation, or that is the phenomenon of a moving wave. If you look at a snapshot of it in time, at any time, the shape of the wave with respect to position is sinusoidal. If you look at a point in space, imagine looking at a swimming pool, and there's a beach ball in the swimming pool, and you're looking at the height of that beach ball. As the wave goes by, that beach ball goes up and down sinusoidally. So the equation for a traveling wave has a position function that varies sinusoidally and a time function that varies sinusoidally. The solution of that wave equation is that the electric field as a function of time is equal to some amplitude times the sine of kx minus omega t, where k and omega are related to these constants mu and epsilon. So what did Maxwell, quote unquote, discover? Maxwell discovered that if you take the equations of electromagnetism and perform a little calculus wizardry on them, you get a wave equation for the electric field. By the way, I could have chosen to eliminate, instead of eliminating B from this equation, I could have chosen to eliminate E from this equation, and I'd get an analogous equation for the magnetic field. But whichever one you eliminate, you get an equation that describes a traveling wave in space, and that wave's amplitude is just the strength of the electric field. Which means it is possible to have in empty space an electric field that oscillates sinusoidally, first pointing in one direction, and then pointing in the other direction, and then pointing in the other direction, and so on. Since the relationship between E and B is that of a cross product, that also creates a magnetic field perpendicular to the electric field that also varies sinusoidally in space. So you have a situation where there is an electric field that oscillates from point to point and time to time, and a perpendicular magnetic field that oscillates from point to point and time to time, that propagates through space at a velocity determined by this equation. The next thing Maxwell did is he computed the velocity of this wave. The velocity of this wave is equal to 1 over the square root of mu0 epsilon 0. That just falls right out of the wave equation. Okay, the velocity of this wave is 1 over the square root of mu 0 epsilon 0. The values of those fundamental constants were known from Amperes Law, and from Gauss's law, from Coulomb's law. So Maxwell took mu 0, epsilon 0, multiplied them, took the square root, took 1 over that, and he got a number, 300,000 kilometers per second. Okay. That number would have been familiar to Maxwell in the 1800s. We have known since the late 1600s, I think at least the early 1700s, what the speed of light is. And the speed of light is 300,000 kilometers per second, 3 times 10 to the 8th meters per second. So Maxwell recognized that the speed of propagation of this wave of electricity and magnetism was the speed of light. It is a very small logical leap to go from there to the result that what this electromagnetic wave is, this wave of electricity and magnetism, is light. That light is nothing more or less than a wave of electric and magnetic fields propagating through space, the electric field creating a magnetic field, the magnetic field creating an electric field, the electric field creating a magnetic field, varying in space and in time according to a wave equation and propagating through space with a velocity of 3 times 10 to the 8th meters per second. So this is not only the result of Maxwell's equations, this is the secret word. The secret word is light. Okay, so if you've watched the video this long and there's a question on the final exam that asks, what is the secret word? The answer to that question is the secret word is light. Maxwell discovered, not experimentally, by the way, purely mathematically, that light was an electromagnetic wave, or rather, I mean, we had to prove this experimentally. Eventually, let's be really clear about what Maxwell did. Maxwell discovered that you could, from the equations for electricity and magnetism in free space, find a wave of electric and magnetic fields that propagated through space at the speed of light. Therefore, it is a very small logical leap to guess that all light is this wave of electricity and magnetism. Not only that, but you should be able to make electrical and magnetic waves by having changing electric fields at any old frequency you want. So if you take electrons and make them, say, move up and down in a wire by passing electrical current through a wire and having those electrons move up and down, that should create an electric field that changes in space and time, that creates a magnetic field that changes in space and time, that creates an electric field, that creates an electromagnetic wave that propagates through space. If you put another wire over here filled with electrons, they should experience an electric field that points this way, then this way, then this way, then this way, then this way, and the electron should move back and forth in the wire according to the amplitude of this wave as it passes by. This is, if you do this a few hundred times to a few thousand times a second, this is radio, the first transmission of an electrical signal from one end of the lab to the other was done by Hertz, after whom we have named the unit of frequency. So only a few decades, maybe less than a decade, I have to look up the dates on this, very shortly after Maxwell proposed the idea of electromagnetic waves, people like Hertz started making them, and it was only a few decades after that before we started using electromagnetic waves like radio waves for communication. This is important because we really didn't have a very good sense of what light was before Maxwell. I think we talked a little bit last semester about the idea of the luminiferous, this is making me crazy, speaking of light, the idea of the luminiferous ether. The luminiferous ether being the substance that fills up all of space. And just like sound is a vibration of the air, light would be a vibration of the luminiferous ether. The idea of luminiferous ether never really made a whole lot of sense because the properties it would have to have would be so bizarre in terms of the fact that it has to interact with matter. Because I can light a candle and it gives off light, so somehow that matter is making the luminiferous ether vibrate. But it doesn't have any resistance to motion. The Earth orbits the Sun through the luminiferous ether and doesn't slow down or experience any friction or spiral into the Sun. So luminiferous ether was not a great model for the medium of light. What we decide post-Maxwell is that light doesn't exactly need a medium. The medium of light is just the electric and magnetic fields themselves. That what light is an oscillation of the electric field in space, not some substance in space. So we don't need to postulate the existence of a material ether any longer because we have this oscillating electric field and magnetic field instead as an alternate thing to be the thing that is oscillating. This all leads eventually to Einstein's theory of relativity. And I won't give a whole lecture on relativity now, although I could and I would love to. I will say just this, that there's something funny about Maxwell's equations, which is we assumed we were in empty space, and that's all we assumed. No charges, no currents. I lost my eraser, that's why I'm looking around like a crazy person. Oh, it's right here on the floor. And the speed of light is built into this differential equation. And these constants, mu 0 and epsilon 0, are just properties of empty space. Remember, their names are the permittivity of free space and the permeability of free space. They're just constants for our universe that tell us how much electric field we get for a certain amount of charge and how much magnetic field we get for a certain amount of current, just like Newton's big G in the law of gravitation. F is gmm over r squared. It's just a property of the universe that tells us for a given amount of mass how much force do we get. The fact that Maxwell's equations say the speed of light is c equals 1 over the square root of mu 0 epsilon 0 equals 3 times 10 to the 8th meters per second is weird. Nowhere else in physics will you find an equation that says the speed of this thing is some number. Why? Because speed, if we go all the way back to Galileo, is relative. Right? Speed and velocity are only meaningful terms relative to some reference frame or some observer. We talked about this fact way back in the beginning of first semester when we talked about the fact that Galileo had to establish the relativity of velocity to argue against Aristotelian physics and support the Copernican worldview, the idea that the Earth goes around the sun and not vice versa. So to say that the speed of a car is 60 miles per hour, what you mean is the speed of the car is 60 miles an hour relative to the road. It's 1,000 miles an hour relative to the center of the Earth because the Earth is rotating. It's 10,000 miles an hour relative to the moon because the moon is going around the Earth. It's 100,000 miles an hour relative to the sun because the car is on the Earth, which is spinning and is going around the sun. It doesn't make any sense to say the speed of the car is whatever. Speed is not a property of the car. It's a property of how that car is moving relative to some reference frame or relative to some observer. Nonetheless, Maxwell's equations seem to say, if you use Maxwell's equations, they will tell you that the speed of this oscillating electric and magnetic field is this number, which is based on nothing more than the properties of free space. It doesn't say anything about observers. It doesn't say anything about reference frames. It doesn't say anything about velocities of anything other than the light. In fact, the fact that it does this means if you take Maxwell's equations, div E equals rho over epsilon naught, div B equals 0, curl E equals minus dB dt, curl B equals mu 0 I plus mu 0 epsilon 0 dE dt. If you take those equations and put them in a moving reference frame, and ask two observers to calculate, say, what's the electric field or what's the magnetic field due to some arrangement of charges and magnets. I lost my other observer over here. I've got a stationary observer down there at the bottom. There they are. What you will find is that if this reference frame is moving with some velocity v relative to this reference frame, that the two observers will not agree on the correctness of Maxwell's equations. The fancy way we say this is that Maxwell's equations are not invariant under a Galilean transformation. In other words, if you change all the x's in Maxwell's equations to x plus velocity times time, put them in a moving reference frame, you get junk. You get a situation where two different observers will disagree either on the speed of light or they'll disagree about whether or not Maxwell's equations are right. You can't have it both ways. Reconciling this fact, reconciling the discrepancy between Maxwell's electrodynamics and classical relativity, the idea that all observers should agree on the laws of physics, including the speed of light, because the speed of light is now special. The speed of light is not like the speed of a baseball or the speed of a truck or the speed of a planet. It is based on fundamental constants of the universe. So when Einstein came along, what Einstein did was say, look, we have to understand relative motion in such a way that we preserve the invariance of Maxwell's equations and the invariance of the speed of light, so that any two observers, no matter how fast they're moving, will agree on C. And I think we talked a little bit about relativity last semester. Sometimes I like to toss in a little relativity lecture in first semester. But Maxwell's equations are important not just because he added an extra term about the rate of change of the electric field. Maxwell's equations are important because he discovered that light is an electromagnetic wave, that there's a whole spectrum of other electromagnetic waves that we can create and observe in addition to light. And his equations forced us to establish a more precise theory of relativity. They forced us to establish a way to deal with moving reference frames in which not only did all observers need to agree on the laws of Newtonian physics and F equals ma, and every action has an equal and opposite reaction. All observers had to agree on the constancy of the speed of light, because the speed of light itself is a law of nature. Okay, so I'm going to leave it there. Like I said, it would be great to have another couple lectures on electromagnetism and show how the Lorentz transformations preserve the invariance of Maxwell's equations. We don't really have time for that. You'll do that in a modern physics class. You'll do that in an advanced E&M class. For now, though, I did want to at least talk about Maxwell's equations so you can see, first of all, what they look like, because you'll see them again probably in the future if you keep taking physics classes, and so you could understand the historical importance of what Maxwell did.